So in this video, we're going to introduce aromatic compounds. And aromatic compounds are, I'm not sure if you've heard of the molecule benzene, but they are benzene-like compounds. So these are like benzene. I'll draw out what that looks like in a sec. These are not typical alkenes or trienes or whatever. So these are benzene-like compounds. And with benzene, I'm going to just draw the line bond structure. We have a six-membered ring, and each of the carbons is sp2 hybridized. So with these particular compounds, we typically refer to them as either aromatics or sometimes you might see it referred to as an arene. So aromatic compounds are different than aliphatic compounds. Aliphatic compounds are like if we had, for example, an alkane, an alkene, or an alkyne. We refer to them as aliphatics. Just in case you run into that terminology, an aliphatic compound comes from Greek origins, where it refers to kind of like an oily or a fatty sort of compound. So an alkane, alkene, or an alkyne, or their groups are referred to as aliphatics. Aromatics are quite different. Their reactivity is very different. They are extremely stable. Busting up aromaticity is energetically unfavorable, and so therefore these particular compounds do not react the same as a typical unsaturated hydrocarbon. So in terms of benzene, and the notes that I have shared go into greater detail about this, but just a couple of sort of characteristic things about benzene. Each of the carbons, so each carbon has a p orbital, so it's an unhybridized p orbital. And so that unhybridized p orbital is going to be used to create a pi bond, but this unhybridized p orbital is laying sort of perpendicular to the sigma bond in the ring. So each carbon has an unhybridized p orbital perpendicular to the sigma bond, the carbon-carbon sigma bond in the ring. And so those p orbitals are going to overlap to form pi bonds. And so what you get is sort of like a cloud, or like an uninterrupted cloud. It's a conjugated pi system, but it's an uninterrupted cloud of pi electrons. So each unhybridized p orbital will overlap to make a pi bond, and this is going to result in an uninterrupted sort of cloud of pi electrons. The molecule is flat, and the word that we use for that is planar. So each carbon is sp2 hybridized. And the other thing that we notice is that the pi cloud contains, and we'll get into the criteria for aromaticity in a sec, but the pi cloud contains an odd number of pi electron pairs. Not an odd number of pi electrons, but an odd number of pi electron pairs. So then let's just take a little peek, because your book doesn't really go into, in this class, we're not going deep into aromaticity and can you recognize if a molecule is aromatic. I just want to just briefly show you, you can be staring at a molecule that looks like it might be aromatic and it's not. And there's actually 3 categories, not just aromatic or not, but there's a third category of compounds. And so we've got criteria for aromaticity. So is a molecule aromatic or not? We have a little list, of course. You need a cyclic molecule. So you need a ring. You need for it to be flat. So it needs to be planar. You need to have a conjugated pi system. So an uninterrupted cloud. So a conjugated pi system of electrons. And we have this other rule, Huckel's rule, where if n is any whole number, 4n plus 2 is going to equal the number of pi electrons. And if your number of pi electrons does not come out to some sort of 4n plus 2, then you are not an aromatic compound. So let's just look at an example. We'll use benzene to start. So we draw out the line bond structure of benzene. We have a ring. Every other carbon-carbon bond is a double bond, which means we have an uninterrupted or a conjugated pi system. So let's just check off our list here. We are cyclic. It is a ring. It is planar. Each carbon is sp2 hybridized. There are no puckers, so we have a flat situation going on here. We have a conjugated pi system, so our pi cloud is uninterrupted. So the first 3 criteria we can check off the list, and then the very last thing you want to check is to make sure it obeys Huckel's rule. So in other words, I see that I have 3 double bonds, or in other words, I have 6 pi electrons, right? So 4n plus 2 is equal to 6 pi electrons. So n is a whole number. So up here, n is going to be any whole number. There are some molecules that look like they might be aromatic, but they're actually not. So for example, we could do like, we have a cyclic compound here. So yes, this is cyclic. It is planar. But check it out. So your double bonds are not conjugated, right? And how do you know? So if I were to move the electrons between, say, these two carbons and put it between these two carbons, I would put a charge on the species, wouldn't I? I'm moving electron density away from this carbon here. It would put a positive charge there, right? I have two hydrogens on that other carbon, so I have too many electrons around that carbon at the top there if I were to move those electrons, right? So that's not okay. So in other words, I don't have a conjugated pi system. So immediately this is not an aromatic compound. And so if you hit a one of the criteria and you don't actually meet it, so we're cyclic, we're planar, but we're not conjugated, then the number of pi electrons is not relevant. In other words, this is not an aromatic compound. So benzene is aromatic. But cyclopentadiene is not. So not aromatic. So there's aromatic, there's non-aromatic or not aromatic, and then there's a third category called anti-aromatic. And you might be wondering why we care about those, because if you're either aromatic or not aromatic, why bother with a third category? Well, here's the deal. With the aromatic compounds, they are quite stable, meaning they're relatively unreactive. You can get them to react, and they do have a characteristic sort of celebrity reaction that they undergo, and we're going to talk about that. The non-aromatic compounds are kind of mildly unstable. They're not as stable as an aromatic compound. You don't have that conjugated pi system. They're not like super reactive, so they're not wicked unstable, right? So they're weakly reactive or mildly unstable, but there's a third category of compounds that look like they belong in this category. Something like this, where you have a ring, so it is cyclic. It's flat, so this is planar. But here's the thing. You have, and it's conjugated, right? So you can zip these around the ring, these electrons. So I meet all three criteria for aromaticity, except the fourth rule, Huckel's rule, actually doesn't apply here. These follow the 4n rule, where n is 1 here. I have 4 pi electrons. So n is equal to 1, and we call this anti-aromatic. What is the difference between anti-aromatic and non-aromatic? Well, so aromatic compounds are extremely stable, right? They're relatively unreactive. I mean, they react, right? But you need some harsh conditions, or you need to encourage these to actually react, right? So you get that conjugated pi cloud of electrons. Then there are the compounds that are just not aromatic at all. They look like they might be, right? They're cyclic, they're planar, but we don't have a conjugated pi system there with cyclopentadiene. So these are not nearly as stable as aromatic compounds. So they're kind of like weakly reactive, right? And then there are the anti-aromatic. So if you think like aromatic is really stable, non-aromatic is sort of like mildly unstable. Anti-aromatic are really unstable. They're highly reactive. So these are really unstable. And for us, that means they're really reactive. So this is sort of mildly unstable. When we say unstable, we don't mean like this is going to blow up in your face kind of a thing. This is just, we're talking energy, right? So if I say that something is really stable, it means just generally that it's unlikely to react, or you need to encourage it to react. When we say something is really unstable, it just means that it's really reactive. And so we're not spending a ton of time in this sort of little area of the world here. I just wanted to show you the difference between three molecules that look like they could all be aromatic. So don't get used to seeing these like double bonds in a ring and think everything's aromatic, because that's not the case. So we have rules that separate the non-aromatic compounds from the aromatic compounds, and then we have the anti-aromatic category. In terms of naming these, so we have a few rules. Simply, if you have one single substituent on the ring, so if I've got, just say, for a monosubstituted benzene, or in other words, you have benzene with a single substituent on it, you're just going to name the substituent and follow it up with the word benzene, right? So we've got something like a bromo group and then your aromatic ring. This right here is just bromobenzene. We could have a nitro group. I pick on this top position. It doesn't really matter. At the end of the day, we only have one substituent on the ring, right? Could be anywhere. This is nitro. That group is a nitro group, nitrobenzene. But I know that you could probably imagine that we're not rolling around with just one single substituent on a benzene ring all the time, right? So, and some of these actually have common names, so should probably sort of like spend a little time talking about those. So some monosubstituted benzenes have common names. And we can use these common names in IUPAC nomenclature. So we're allowed to do that. And you'll see in a bit when we have more than one substituent on a ring, they'll be sort of named as almost like a little family of compounds. So for example, I could have like the amino group attached to a benzene ring. And we refer to this as aniline. I could have a hydroxyl group. When we hit amines and alcohols, when we get into those functional groups, you'll see that aniline is not the same as, say, cyclohexylamine. It's not just a ring with double bonds and then the amino group. They absolutely do not behave the same way. One of them is more acidic than the other. It's a little less reactive than the other. So it's definitely its own thing. If I put the hydroxyl group on a benzene ring, it's not a garden variety alcohol. It's an aromatic alcohol. This is actually referred to as phenol. We could swap out that hydrogen on phenol and put a methyl group that has its own category. Sometimes you might see a little circle in the middle of the ring instead of the three double bonds. And really, all that's telling you is that your pi system is conjugated, right? And the other thing it kind of describes nicely is the resonance hybrid. So if you were to get bond energies for each carbon-carbon bond in the benzene ring, you'd have like one value, even though it looks like when we draw every other bond a double bond, it looks like, hey, shouldn't this single bond be, longer and lower in energy? When you actually do a computation to figure out the energy, or if you were to try to reduce this thing, right, and measure the difference in energy, between the benzene ring and say cyclohexane, you'd notice a big difference in energy. And so we could figure out the bond energy, and it turns out you get one value. So that little circle that you might see, very often you see it in almost like I guess like an anatomy and physiology textbook, or maybe a biochemistry textbook. They're just trying to indicate that you have a conjugated pi system. So this right here, this OCH3 attached to a benzene, this is anisole. And if you've ever worked in a lab or any sort of situation where you've used particular reagents, organic compounds before, you might be familiar with some of these names. Oh, this one, a lot of people have heard of this one. If I put a methyl group, so here I'll put the little circle so you can see what I'm talking about. That's the same as drawing the 3 double bonds. This is toluene. It's a typical nonpolar solvent. What else can we draw for you? Could draw what you might want to call vinyl benzene. This is styrene. That's the common name. I'm sure you've heard of polystyrene, right? We can polymerize this. We end up with polystyrene. We could have, we'll draw just a couple more before we move on. This is benzaldehyde. And this last one I'll draw is benzoic acid. So those are common names that if we were to stick another substituent on the ring, we would name it for these common names, as if these are their own little family of compounds, right? So if I put like a chloro group on the ring somewhere, I would name it as a chloro substituted phenol, right? I wouldn't name the hydroxyl group separately. So with the exception of toluene, your alkyl substituents, if you have like an ethyl group or a T-butyl group or something like that on the ring. So with the exception of toluene, so a methyl substituted benzene. So with the exception of toluene, because we refer to that as toluene, if you have an alkyl substituent, you're going to name, if you're using common nomenclature, you're going to name those compounds as alkyl substituted benzene. If you're naming them IUPAC style, so like a systematic nomenclature style, you're going to refer to the aromatic ring as a phenyl group. And I'll give you a couple of examples of that. So for common nomenclature, it's an alkyl substituted benzene or a phenyl substituted alkane, or, so this would be IUPAC, or whatever the other parent would be. So for example, if you had another compound that would take priority over the alkane, like if it was like a carboxylic acid or something like that, you would refer to the benzene ring as a phenyl group. If you have a benzene ring and then it has a methylene attached to it, a CH2, and then you've got some other stuff going on, that's actually a benzyl group. So we have a phenyl group, which is just the ring. We have a benzyl group, which is the ring plus a CH2 and then rest of your stuff. So those are actual sort of common names that we use in IUPAC nomenclature. So for example, I could have something like this. Again, you could draw those double bonds as just a little circle. I could refer to this as tert butylbenzene. That would be common nomenclature, right? So the alkyl substituted benzene. Or if I wanted to name it IUPAC style, I would have to name this as, I have to find my longest continuous chain of carbons, and the phenyl group or that benzene ring would become a substituent. So I would have 2-methyl, and you would just name this like you normally would, putting them in alphabetical order, separating the numbers and words with hyphens. And this is all one word. So my longest continuous chain would be those 3 carbons across the top. Off of carbon 2, I have a methyl, and then again off of carbon 2, I also have a phenyl group. The phenyl group is right here, is this right here, if you're using IUPAC nomenclature. I could have something like this. Oops. And we could put the benzene ring on this carbon here. So if I'm using common nomenclature, that CH2 with the aromatic ring is referred to as a benzyl group. So it's the phenyl ring, right, with the methylene. That's a benzyl group, and this would be benzyl chloride. Or I could say this is named after the alkane, and my longest continuous chain of carbons, if I'm using the phenyl group as a substituent, is simply just 1 carbon. So this becomes a chlorophenyl methane. This molecule is usually just called benzyl chloride. So common names are used because they're common, right? It's not wrong to use IUPAC nomenclature, but very often you'll see the common names. What else can we think about here? If you've got 2 substituents, so if your ring has 2 groups, we can use, instead of saying the number of the carbon, we can use ortho, the words ortho or the prefix ortho, meta, or para to indicate position relative to each other on the ring. So don't try to do this if you have more than 2 groups. I've seen students do that before, where they'll put like meta and then they'll start naming their group. You can only have 2 groups if you're telling somebody what their position is using ortho, meta, and para, because what this refers to as These groups would be in the 1, 2 position relative to each other. These would be 1, 3, or these would be 1, 4. So you can't have more than 2 groups on the ring and then use those prefixes and have them make any sense. So for example, if I've got like a chloro group, and by convention, it's not necessary that this happens, but if they're the same group, usually the one that's up there, if you're looking at this like it's a clock, the one at the top there at noon is position number 1. If I've got 2 chloro groups in the 1, 2 position, we refer to these as ortho. It's not wrong to say 1, 2 dash dichlorobenzene, but ortho, or in other words, just a little O dash dichlorobenzene, the word ortho or the little O would tell somebody they are in the 1, 2 position relative to each other. Meta would look like this. So like in the 1, 3 position. So here's meta. If you were to name this, you would either say 1, 3 dash dichlorobenzene, or you could say meta dash dichlorobenzene, or just a little m is fine too. And then the last one is if you've got 2 substituents on the ring and they are in the 1, 4 position relative to each other, they are para. So this would be para dichlorobenzene, or you could just put a little lowercase p and then a hyphen and then dichlorobenzene. What if I have 2 groups on the ring and they're not the same? So if I have 2 groups on the ring and they're not the same, I can still use this ortho meta para nomenclature, but I'm just going to put the groups listed in alphabetical order, that's all. So if I had something like this, just to switch things up a little bit. So I have an iodine there on one of the carbons. I have a fluorine on one of the other carbons. They are in the 1, 3 position relative to each other. So this is meta, or you could just have a little m, fluoro, iodobenzene. So you just alphabetize them. That little m tells somebody that they are 1, 3 relative to each other. One of them is on carbon 1, the other one's on carbon 3. And if I've got more than 2 groups, so what if you have more? So if I end up with more than 2 substituents on the ring, then you're just going to use numbers. Don't use ortho, meta, or para. It doesn't make any sense. So if you're going to put, say, for example, some groups on toluene, so I'll put a nitro group here, stick a nitro group there, and a nitro group there. So this will be named as a tri-substituted toluene. The toluene means that the word toluene means I've got the methyl group on the benzene ring, and so therefore that means that that is carbon number 1. So relative to that, I have 2, 4, 6 tri nitro toluene. So this is a situation, remember, where we're using common nomenclature. The toluene part is the common nomenclature, and that refers to the benzene ring with the methyl group on it. The trinitro with the 2, 4, 6, that's IUPAC style. The second you start seeing numbers involved, that's IUPAC. But toluene is a common name, so we can sometimes overlap these and just sort of fold them together into sort of like a hybrid nomenclature. So this is 2, 4, 6 trinitrotoluene. often you'll just see this referred to as just simply TNT. So if you have a ring that's got more than two groups on it, you're going to use numbers and you're going to alphabetize them. So if those weren't all the same substituent, you would just list them in alphabetical order. And if you're wondering which number to give, so if they're all sort of like in the same position, like I've got three totally different substituents on carbons 2, 4, and 6, then I'm going to give them the lowest possible number in alphabetical order. So if I had like a bromo, a fluoro, and an iodo, I would put the bromo group on carbon number 2, because you could count in either direction around the ring. So that's sort of like your last sort of resort if you're naming these things and you're like, well, I could put the bromo group on carbon 6 or I could put it on carbon 2. Well, if you don't have any other reason, um, you know, like you don't have other functionality that takes priority on the ring, then your lowest number is going to go to your substituent that comes first in the alphabet. So that's how we name our aromatic groups, our aromatic molecules. In the next video, what I'd like to do is discuss the reactivity. There's one sort of celebrity kind of reaction that we're going to focus on with aromatic compounds. I want to give you a few examples, and then we need to talk about, hey, what happens when you want to do chemistry on an aromatic ring? It already has a substituent attached to it. Like, where is this incoming group going to go if we want to attach another group? So say, for example, you wanted to make 2,4,6-trinitrotoluene. What would you start out with, right? How would you begin that synthesis? So that's sort of where we're headed in the next video.